Hello everyone, I'm Dr. Manju Gupta, Department of Chemistry, St. Aloysius College. Today I'm going to discuss chemical reactions or chemical properties of the alcohols. Alcohols are considered as central functional groups. Why it is considered as a central functional group? Since all other functional groups can be obtained from alcohols. For the preparation of other functional groups, alcohols is always used. For example, alkenes can be formed by the dehydration of alcohols. Ketones, aldehydes are formed by oxidation. Halides can be formed by substitution. Alkenes can be formed by reduction. By esterification, esters will form. By tosylation, tosylate ester will form. And by the reaction of alkyl halide, it is also converted into ethers. Here, today we will discuss some main chemical reactions of the alcohols. First main reaction of alcohol is oxidation of alcohol. Oxidation means addition of oxygen or elimination of hydrogen. These are the different oxidizing agents which can be used for the oxidation of alcohols. Aqueous oxidant like chromic acid, chromate salt, dichromate salt, or permanganate. These oxidizing agents are soluble in water. Whereas anhydrous oxidant, pyridinium chlorochromate or pyridinium dichromate, these are the two anhydrous oxidants. First, we will discuss oxidation of primary alcohols. Oxidation of ethanol or primary alcohol to aldehyde or acetaldehyde. Aldehydes are more easily oxidized than alcohols and they are converted into carboxylic acid. It means generally by the oxidation of alcohol, oxidation that means addition of oxygen or elimination of hydrogen. In the first step, by the elimination of hydrogen, aldehyde will form, and if the alcohol is primary or simpler alcohol like methanol or ethanol, these aldehydes are easily again oxidized to carboxylic acids. For the oxidation, we can use chromic acid. Chromic acid is too reactive and the aldehyde formed cannot be isolated. As it formed, it is oxidized immediately into the acid. So finally, by the oxidation of alcohol, we get corresponding carboxylic acid. By the oxidation of ethanol, final product will be the ethanoic acid. For the oxidation of primary alcohols, we can also use pyridinium chlorochromate. This is the structure of pyridinium chlorochromate. Pyridinium chlorochromate oxidizes primary alcohol in dichloromethane and convert it into aldehyde. Since it is a weaker oxidizing agent, so it is not strong enough that it can oxidize the aldehyde. So the reaction can be stopped at the first stage, that is formation of aldehyde, when we are using the weak oxidizing agent or pyridinium chlorochromate. Oxidation of secondary alcohols. Secondary alcohols are oxidizes into ketones. The common reagent used for the oxidation is the chromic acid. Secondary alcohol with chromic acid converted into ketones. Cyclohexanol is converted into cyclohexanone. Pyridinium chlorochromate will also transform a secondary alcohol into the corresponding ketone. It means only here is no formation of any intermediate. So PCC or pyridinium chlorochromate will also transform, can also convert secondary alcohol into corresponding ketone. Since in the tertiary alcohol there is no CH bond, so tertiary alcohol cannot be oxidized to carbonyl compound, as it would involve the breaking of one carbon-carbon bond in this process. So oxidation of oxidation of alcohols can be used for their uh, differentiation. Here, these are the chemical reactions used to differentiate. Primary alcohols lastly form converted into carboxylic acids. Alcohols are converted into ketones, and tertiary alcohols are not form a product after the uh, oxidation reaction. Second property or second chemical reaction. Second chemical reaction is the dehydration of alcohols. Dehydration, as the name indicates, D that means removal, hydration that means water. From the alcohol, removal of water molecule. Water molecule can be removed by anhydrous salt or dehydrating agent. When alcohol heated with a strong acid catalyst by dehydration, it is converted into alkene and water. A strong acid catalyst in this reaction, concentrated sulfuric acid is used as the dehydrating agent. And this process of dehydration of alcohol will form alkene according to the Sedgwick rule. What is the Sedgwick rule? Sedgwick rule is applicable in case of unsymmetrical alkene. In case of unsymmetrical alkene, the two products will be possible. As you can see, the dehydration of butanol. By the dehydration of butanol, two products can be formed, 1-butene and 2-butene. The major product of the reaction favor the more stable alkene, or we can say the more substituted alkene formed as the major product. By the dehydration of 2-butanol, two possible alkenes can be formed. 1-butene, in which double bond is present in between first and second carbon. First carbon is attached with 2 hydrogen. Second carbon is attached with 1 hydrogen and 1 alkyl chain. In case of 2-butene, both the carbons are attached with 1 hydrogen and 1 methyl. So we can say the double bond present in the 2-butene is more substituted. So it will form as the major product, and this will be the more stable alkene. Main thing is that dehydration reaction follows the Sedgwick rule. Alkenes are formed via even mechanism. Even, that means elimination unimolecular. In this, carbocation rearrangement is the key step, especially for primary alcohols. Rearrangement of carbocation, that means if carbocation is generated at the primary carbon or secondary carbon. Since if we discuss the stability of the carbocation, tertiary carbocation is more stable than secondary, and secondary is more stable than primary. So if primary and secondary carbocation is formed as an intermediate during the reaction, it will automatically rearranges into the more stable carbocation. That means primary can rearrange into secondary or tertiary, and secondary can rearrange into tertiary. Dehydration of 1-methyl cyclohexanol. This is secondary alcohol. Tertiary alcohol. First step is the protonation. Protonated alcohol will form. After the protonation, there is the removal of water molecule and it is converted into the carbocation. This carbocation is already tertiary. This carbocation, dehydration, that means removal of water. One water molecule is removed. Now, by the H2O, you can see there are two different sets of hydrogen, HA and HB. Oxygen eliminates one HB proton and one HA proton, and there is the formation of carbon-carbon double bond. Finally, there is the formation of two products can be formed. First, when loss of Ha, this hydrogen is removed by the oxygen, and second, when Hb is removed by the hydrogen. When more substituted double bond will form, that will be the major product. If Hb is removed, this double bond is formed when a single double bonded carbon have two hydrogen. But in case of second condition, where Ha is removing the double bonded carbon, only one carbon has one hydrogen. Otherwise, all the two double bonded carbon atoms are connected with other carbons. So it is more substituted. So it will be the major product of the reaction formed in the higher percentage. Third reaction. Third reaction is the halogenation of alcohol. When alcohols react with hydrogen halide, a substitution reaction takes place and producing an alkyl halides and water. Since hydroxide ion and halide ion both are acting as nucleophile, so this is a nucleophilic substitution reaction. If we discuss the order of reactivity of alcohols, tertiary alcohols are more reactive for halogenation, then secondary, and then primary. And in the last, methyl alcohols. And if we discuss the order of reactivity for the hydrogen halide, hydrogen iodide is more reactive, then HBr, then HCl. Hydrogen fluoride is generally unreactive. Primary and secondary alcohols can be converted into alkyl chlorides and bromides by allowing them to react with a mixture of sodium halide and sulfuric acid. Mechanism. Nucleophilic substitution, that means substitution of one nucleophile by another nucleophile. Alcohols can be primary, secondary, tertiary, allylic or benzylic. We will discuss the mechanism in the two parts. First, secondary, tertiary, allylic and benzylic alcohols appears to react by a mechanism that involves the formation of carbocation. Carbocation will be the intermediate and the rate of reaction will depend on the concentration of that carbocation. That's why this reaction is substitution nucleophilic unimolecular or SN1 reaction, because the concentration or the rate of the rate determining step of the reaction is the formation of carbocation with the protonated alcohol acting as the substrate. First step is the protonation of alcohols in acidic medium and formation of oxonium ion. The oxygen of alcohol attached with a proton and form oxonium ion, protonated oxonium ion or protonated alcohol. In the second step, protonated hydroxyl group departs as a leaving group to form a carbocation and water. This protonated OH group eliminates as a water molecule when one bond pair remains free from the carbon. It acquires positive charge. So carbon is converted into carbocation by the removal of water molecule. Third step is the carbocation. Formation of carbocation is the slow step, that is rate determining step. In the third step, another nucleophile, that is chloride or halide, can attack on the electrophilic center or carbocation form to form a substitution product. A halide ion reacts with the carbocation. In this reaction, one thing is must to remember, that product will always form with the retention of configuration. That means from the same phase, the nucleophile is eliminated, and on the same phase, another nucleophile is attached. So this reaction takes place with the retention of configuration. This was the case of secondary alcohol, tertiary alcohol, vinylic alcohol and benzylic alcohol. If we consider the reaction of primary alcohols and methanols, alcohols with small alkyl groups, primary alcohols and methanols react with alkyl halides under acidic condition and follows the mechanism SN2 react mechanism. SN2 mechanism, nucleophilic substitution bimolecular. That means rate of reaction depends on the concentration of alcohol as well as on the concentration of alkyl halide. In the first step, first there is the formation of a transition state. Transition state involves the bond formation and bond cleavage simultaneously. At one side, one nucleophile is attacking and from the other side, another nucleophile is removing. So, pentavalent carbon will form for a second, that is transition state, and in this transition state both the species are involved, alcohol as well as alkyl halide. This is the slow step, and the slow step involves two species. That's why it is nucleophilic substitution bimolecular or SN2 mechanism. Here, opposite to the case of SN1, nucleophile attacks to the carbon from the opposite side of the already present nucleophile. So the product will form with the inversion of configuration. The function of the acid to produce a protonated alcohol, the halide ion then displaces a water molecule from carbon and this produces an alkyl halide. So this was the main reaction, nucleophilic substitution or halogenation of alcohols. Fourth reaction is esterification. Esterification is the process or reaction of combining an organic acid, carboxylic acid, with an alcohol to form an ester, RCOOR, and water. In this reaction, generally acid is used as the catalyst and this is known as Fischer esterification. Carboxylic acid in presence of alcohol react with alcohol and form ester. Another example is the reaction of ethanol and ethanoic acid. Ethyl ethanoate will form. By the reaction of methanol and benzoic acid, methyl benzoate will form. Mechanism of the esterification. First step, protonation of the carbonyl carbon by the acid. This carbonyl is now activated towards the nucleophilic attack. Second step is the nucleophilic attack on the carbonyl group. Nucleophile OH minus attacks on the carbonyl group and form an addition intermediate. Third step, there is the transfer of proton from the alcohol molecule to the nearby oxygen. And fourth step, when the proton is transferred from the alcoholic OH to acidic OH, the water molecule can easily be eliminated and it is converted, removal of water molecule and converted into another species. And lastly, formation of ester by deprotonation. Remaining counter ion of the acid will abstract the proton and it is converted into ester. Esterification can also occur when alcohols react with acid chlorides. Reaction of acid chlorides with any alcohol, like a reaction of benzoyl chloride with methanol. It also converted into aromatic ester. Next reaction is the reduction of alcohol. Reduction means elimination of oxygen or elimination addition of hydrogen. If oxygen is eliminated, then it is converted into alkane. And alkane cannot be directly reduced to an alkane in one step. The OH group is a poor leaving group, so hydride displacement is not a good option. However, the hydroxyl group is easily converted into other group that are superior leaving group or better leaving group and allow reactions to proceed. So first we convert OH to better leaving group and then proceed the reduction reaction. One such conversion involved tosyl chloride and the formation of tosylate. These compounds undergo substitution and elimination very easily, often more reactive than alkyl halides. This is the mechanism in which in the first step tosyl chloride is reacted with alcohol and converted into tosylate. This tosylate can undergo substitution or elimination. By substitution, in the first step, nucleophile can attach, and in the elimination, tosylate group can be removed, and by the abstraction of proton by any base, it is converted into alkene. Next reaction is the acidic nature of alcohol. Acidic nature, that means elimination of proton, elimination of hydrogen as a proton. Acidic nature means a compound can, how much easily it can donate hydrogen as a proton. Acidic nature of alcohol is due to polarity of OH bond. The acidity decreases when electron donating group is attached to the hydroxyl group. Electron donating group attached to the hydroxyl group. Actually, reason of acidity is the electronegative nature of oxygen. Oxygen is electronegative, that's why it attracts the bonding electron pair towards the itself, and hydrogen can be eliminated as the H+. If electron donating groups are attached with the OH, they will provide the source of electron, and the electron density on the oxygen increases and the bond becomes stronger. Bond between the oxygen and hydrogen becomes stronger, so the acidity decreases. Oppositely, electron withdrawing group, which can withdraw the electron like halogen, increases the acidity of alcohols. Primary alcohols are more acidic than secondary or tertiary alcohols, and phenol is 100 million times more acidic than cyclohexanol. This part we will discuss in the next chapter. Now, by the due to the acidic nature of alcohols, they can form alkoxide ion because hydrogen can easily eliminated as the proton and oxygen acquires negative charge, that is known as alkoxide ion. This alkoxide ion can easily react with electropositive metals such as sodium and potassium and form a corresponding alkoxide. Recently, methanol and ethanol react methanol and ethanol with sodium metal and form sodium ethoxide. Less acidic alcohols, that means when the alcoholic carbon is sterically crowded or electron donating groups are attached with the alcoholic carbon, then it will react with more reactive metal like potassium and converted into tertiary butoxide potassium. So this was all about the chemical properties of the alcohols. Thank you.